Okay, so we've gone over so far some terminology associated with metabolism, and we've also looked a little bit in detail about glycolysis and the citric acid cycle, glycogen synthesis and glycogen breakdown, as shown on this diagram. And now what I want to talk about a little bit more is the sort of overarching control of all of these cycles, all of these reactions, these pathways. And I want to look at sort of how the decision is made, which pathway is going to be taken by any given molecule in a particular cell. Because what you really need to remember is that this is a living system, and all of these processes are happening all the time, okay? If we take your average muscle cell, whether it's in a mildly fed state or a mildly fasting state, let's just say that you're, an average college student, and you've either eaten lunch or it's been like 6 hours since you last ate. Your muscle cells are still doing everything that's depicted in this diagram, okay? So there's always going to be glycolysis going on, there's always going to be citric acid cycle, there's going to be some fatty acid synthesis because you're well fed, and there's also going to be some fatty acid breakdown because the enzymes are there, right? And if they're substrate, they're going to work on them. The same thing is true with glycogen over here, okay? It's not like your cells are only storing glycogen when you're well fed and they're not breaking any down. And it's not like your cells are only breaking down glycogen when you need more of an energy source. Because there are enzymes that are present, and if there is a substrate that they can bind to, the enzymes will bind to that substrate and they will work on them, okay? So one of the things that is controlling this enzyme action is covalent modification, like I said. So if an enzyme, for example, is covalently modified with a phosphate group, that could either increase its activity or it could decrease its activity. And that is a sort of overall hormonal regulation. That phosphorylation attachment of a phosphate group is controlled by insulin and glucagon. Okay, and what's really driving whether you're mainly having glycolysis and the citric acid cycle, or if you're mainly having fatty acid synthesis and glycogen synthesis, it really has to do with the amount of substrate that's available and the speed of the reactions in any particular pathway in a given direction. So if I take this set of reactions between fructose 1-biphosphate, 1,6-biphosphate, and phosphoenol pyruvate, well, if you have the enzymes that are working more in this direction from reactant to product, then the overall pathway is going to get driven this way, okay? But if the enzymes working in the forward direction are slower than the enzymes working in the backwards direction, then the backwards pathway is going to happen. And that is sort of what's driving the overall direction of the pathways, okay? Something that I have not yet included in this pathway, in this overview, and I will now add on, okay, is gluconeogenesis, because I know that that is a huge point where people are getting confused, okay? So you see here that pyruvate kinase catalyzes this irreversible slow step between phosphoenol pyruvate and pyruvate, okay? So that essentially means that this enzyme cannot be used to go in the other direction, okay? Because this reaction is so energetically favorable that pyruvate will just not go backwards, okay? So when the body needs to make its own fresh glucose, okay, and it's not getting any, what's going to happen is pyruvate is converted to oxaloacetate, okay? And then oxaloacetate is converted to PEP. And it has to take that roundabout step. It has to go around pyruvate kinase in order to go backwards. And then once you have pyruvate converted to oxaloacetate to PEP, then the rest of this pathway can go backwards up to glucose, and that glucose can be exported into the blood. Alright, so if that's the case, okay, if you're reusing this entire portion of the pathway, then how is it controlled? Whether a cell is going through glycolysis, breaking down glucose, or gluconeogenesis, making glucose from scratch. It's really controlled by substrate concentration and enzyme activity. So, as I said, if the enzymes for going through glycolysis are turned up, they're at a higher rate, or they're at a higher concentration, or you have a higher concentration of substrate, the pathway is going to get driven forwards towards pyruvate, towards acetyl-CoA, and towards making ATP. Okay, if the forward enzymes are slower, okay, if they're not acting as much, if there's not as much substrate for them to act on, then this entire pathway will go backwards, okay, towards gluconeogenesis, towards making new glucose. So what I really want to look at, now that we have clarified some of that, some of the direction of these pathways, all right, is I want to look more at the branching pathways about glycogen and fatty acids and ketone bodies and how all of those play a role, and how the body, a lot of people have asked, well, how does the body decide when it needs ketone bodies, okay, when and where, how is that decision modulated? Well, probably one of the easiest ways to think about it, okay, we're going to start with glucose here. Okay, glucose can go through glycolysis, right, to acetyl-CoA. And then it can go through the citric acid cycle in order to make ATP eventually, okay? Well, what else can feed in? We know that fatty acids can feed into acetyl-CoA, right? Sorry, let me get that actually in the frame. Okay, what else do we know? Well, we know that glycogen can also feed in halfway through this glycolysis pathway. And that can also be turned into acetyl-CoA, right? And it can go down the citric acid cycle and the electron transport chain in order to make ATP. Okay. We also know that acetyl-CoA can be converted into ketone bodies. For clarification, these are also called volatile fatty acids. Okay. That's just a reference to their chemical composition. Alright, so we have, it seems like, this network of pathways. It's completely unwieldy. How does the body decide what it's going to do? Well, it's really all about supply and demand. Okay, if we just forget about the enzymes for a second, I know I've been harping on about those, but if you forget about the enzymes, okay, and you just look at the pathway, imagine that this is a pipe system, okay, and the end of these are spigots, okay, or, you know, partway through any of these pathways there are valves that are controlling the speed of these pathways, alright? So if we, let's say that the body is not getting enough glucose, okay, so this pathway is for some reason shut off or decreased, okay? This link, it just doesn't exist anymore, and there's a blockage. It's like if you get a blockage in the drain, nothing's going through, okay? Well, what the body's going to try to do, if you're in a starvation state, and you should be getting glucose, you should be getting energy, is that it will try to maintain the rate of these reactions, these pathways, okay? It still needs to make the same amount of ATP, okay? The demand has not changed, but the supply has, okay? Well, what happens when that's the case? Well, let's say that you had 100% of your energy coming from glucose. This would never be the case, but let's say you had 100% of your energy coming from glucose. Well, now some of that 100% is going to have to be made up by burning fatty acids, and some of that 100% is going to have to be made up by burning glycogen, okay? So those pathways will automatically start happening a little more, right? Because suddenly this has been shut off, and now these substrates are at a higher concentration, and the body will burn them because it's pulling acetyl-CoA right through this spigot or into the cycle in this case, and the concentration of acetyl-CoA has to be replenished. It's going to be replenished from fatty acids and from glycogen. In addition, the body has all sorts of compensatory mechanisms, so these pathways, breaking down glycogen, breaking down fatty acids, those will be upregulated in order to go faster, all right? Well, then you say, what if you block off the supply of glycogen? Or what happens if you block off what's happening in the citric acid cycle? Then you're going to get a backup at a different point in the pathway, and anywhere that you have another pathway branching off of it, something is going to happen to the rate of those reactions in order to get to the same endpoint of substrate, okay? So if you look at the sort of overview of metabolism, then you can apply that concept to pretty much any of the pathways. As long as you know where they connect, then you can understand what a blockage or what an increase in substrate, decrease in substrate, change in enzyme activity, what that will do to the related pathways. Because the important thing to remember is that all of these pathways, right, they're all going on in any given cell in the body, and most cells have access to most of these things that we've been talking about. So what I would try to do in studying metabolism and seeing how all of these things relate to each other is just think about all of these pathways like a spigot, okay? So you can have one for making energy for starvation, say, requiring energy, requiring ATP, and going down this way. And then you can have another spigot for, well, what happens if the body is well fed? How does it decide whether it's going to make glucose, whether it's going to make fatty acid or glycogen? And see what happens when you change the inputs.